Hi, this is Mr. Coombe. Now we're going to talk about a second type of one-dimensional motion that is a little bit different. We're talking about when things go up into the air and what they do, and how do we calculate different bits of data. So let's look at this type of particular problem. So I used to play footy, and this could be another story that I could tell you guys, but I actually played against Buddy Franklin. For those guys who know about AFL footy who are watching this video. So Buddy Franklin kicked a footy straight up into the air at 29.4 meters per second. We want to find out three things. How long does it take for the footy to come back down to Buddy? And how fast is it going when it comes back to Buddy? And how high he actually kicked the ball. So here's my awesome diagram. So here you have our goals. There's the behind posts and the goal posts. Here's our Buddy Franklin. Kicks up the footy at 29.4 meters per second. So straight off the bat, we should also state our coordinate system. So always, when we're talking about motion in the vertical direction, we should always say that positive is in the upwards direction. Easy. So we know our reference of things, of the motion and what numbers mean when they're negative and positive. Awesome. First things first, we know that the initial velocity, let's put up yellow straight away, initial velocity is 29.4 meters per second. Beautiful. And there's a couple of things that we're actually quite intuitive, being acceleration, we already know. So acceleration is going to be negative 9.8. 9.8 meters per second. Beautiful. So being that the ball will be accelerating in the downwards direction, but if in a positive direction, so when he kicks the ball up, we should be able to logic this out. As he kicks the ball up, the higher it goes, the slower it goes. So the velocity slows down. Okay. Another couple of intuitive things in order to actually have a look at the time. Let's have a look at this actually graphically. Let's make a little data table. Let's say that, because we want to find out eventually, find out what the time is. We want to find out time, how long it took for him to get back down to the ground. We want to also find out how high the displacement of the ball at the maximum height. So at the end of the actual motion, because he's going to kick it up, it's going to get to a maximum height and it's going to come back down. At the end of the motion, the displacement, this should be logical. The displacement is going to be 0 because it came back to where it came from. So the displacement is going to be 0 over that period of time of the motion. So let's have a look at a little table. Let's make a little table here. And let's say that the change in time, let's make it the right color. Let's say that the change in time is in this column. And let's have a look first at the velocity. And let's have a look at, because we also want to have a look at the final velocity at which it gets down to him. But we'll discover a couple of things. So let's have a look at the velocity at any particular time, and we'll also find the displacement at each point in time. Okay, so let's make a little table. Okay. And let's say, just for something random, let's say we're going to do it over 6 seconds. Let's say 6 seconds. So 1, 2, 3, 4, 5, and we have 6 seconds. So let's do the motion over 6 seconds. So first off, let's actually find out how we figure out final velocity. Final velocity, we know that final velocity, let's do that in orange. Final velocity equals the initial velocity plus at, v equals u plus at. But in this particular instance, we know that gravity, so here, we know the initial velocity, I'll put that in yellow, is 29.4, and I won't put in the units again just to save space. And then we actually take that away, because remember our acceleration, let's put that in green, our acceleration is negative 9.8, so we take away 9.8 meters for every second. So for every second that goes along, we take away 9.8 meters per second out of our initial velocity, which makes sense. As it kicks it up, it's going to get slower and slower and slower, and to get to a point, and we'll discover something quite tricky. So let's have a look. If we plug in these values, okay, we should find out at time equals 0, what is his velocity going to be? So time equals 0, it'll be, so this part, so whenever you multiply anything by 0, it's going to be 0, so it's going to be 29.4. Okay, that was easy. At time 1, okay, this is going to be 9.8, so it'll be 29.4, take away 9.8 meters per second. So it's going to be, at time equals 1, his velocity, the velocity of the ball, sorry, not his velocity, the velocity of the ball is going to be 19.6 meters per second. And just for a little bit of clarity, let's put in the units, so time in meters per second. It's a bit hard to do, and our displacement is going to be in meters, and our time is in seconds. Okay. At time equals 2, it's going to be whatever this is. So, sorry, it's going to be 19.6. Take away an additional one, because remember, for every second, we're going to take away 9.8 meters per second from the previous one, basically. So if we take away 9.8 seconds from that one, okay, whoopsie, it's going to be out of control, It's going to be 9.8 meters per second. And if we take away 9.8 seconds for another second, it's at time equals 3. So 3 times 9.8 is actually, I think it's 29.4. So what something here you'll find very interesting. So at 3 seconds, the velocity is going to be 0, which is a little bit, it's going to be something interesting. And let's go further. At time equals 4, it's going to take away an additional 9.8 meters per second. So then you'll find that you'll have a negative velocity here. You'll be at negative 9.8 meters per second. Now that negative, so remember our coordinate system, our positive velocity, which means it's going upwards at that particular time, at time 0 seconds, it's going up at that speed. At time equals 1 second, it's going up at that speed, etc., etc. But at time equals 3, it is no longer going faster. The velocity is 0. But then once time equals 4 comes along, it's actually starting to go down. It's starting to have a negative velocity, meaning it's coming back down. And if we take away another 9.8 away from that one, from additional 1 more second, it's going to be negative 19.6. And at time equals 6, we take away another 9.8 meters per second from that. So it's going to be negative 29.4. So that's quite interesting. So he kicked it up, going at 29.4 meters per second. And he kicked it up, kicked, and after 3 seconds it stopped. And then it started to come back down, and it finished at 6 seconds at exactly the same magnitude. The speed is the same as the initial velocity. However, the direction is now changed in the complete opposite direction. Now the direction is now in the downward direction. Awesome. So if we do a little graph of this, I'd actually really quickly, let's do a quick graph of, let's say, the velocity So velocity versus time. So let's say this is our time, so I'm changing time, and this is our velocity in meters per second, and our time, and our time in seconds. Okay, let's say here is already 6. So 0, 1, 2, 3, 4, 5, 6. So that's 6. This is 1, 2, 3, 4, 5, 6. Very good. So it started off at, let's say that's 30. It's 20. That's 10 meters per second. That's negative 10, negative 20, negative 30. Let's put the actual points in. So at time equals, okay, let's have a look at our table. At time equals 0, our velocity is at about 29.4, so we're really up here. Time equals 1, it's about 19.6. Time equals 2, it's about 9.8. At time equals 3, it is 0. At time equals 4, it's negative 9.8. Time equals 5, it's negative 19.6. And time equals 6, is negative 29.4. And so you should notice that quite intuitively that it is a straight line. Sorry about that little part there. What you should notice as well is that being a straight line, we should be able to also calculate the gradient of this line, and the gradient of this line will be 9.8. It's actually negative 9.8 because we see that it's constantly decelerating. So if you see that the line is on a downward slope, so we know that that's decelerating. Okay, it's a constant deceleration in this particular part. Okay, but in this part it's an acceleration in the negative direction.